Hello, calculus fans. When we compute single integrals, our region of integration is always an interval. You integrate from a to b. For double integrals, we would like to be able to integrate not just over rectangles, but over more general regions. Let's suppose that D, our region of integration, is a bounded region, and all that means is that we can enclose it inside some rectangle. Here's a picture that illustrates the situation. I'd like to be able to integrate over this region, D. It's a bounded region, so it fits inside some rectangle. We're going to define a new function, capital F, with domain R. So little f is the function that we're interested in integrating, but now we're creating this new function, big F. It's defined to be little f if xy is in D, and it's 0 if it's in R but not in D. And then if f is integrable over R, then we'll define the double integral of f over D by saying that it's equal to the double integral over R of big F. So we change the region of integration to a rectangle, and we change it to this piecewise defined function, capital F. Now this definition should make sense because we've already talked about computing double integrals over rectangles. This procedure also makes sense because the values of big F are 0 when xy is outside of D. So that means they're going to contribute nothing to the integral. So it doesn't really matter what rectangle we use as long as it contains D. Now, in the case where f of xy is bigger than or equal to 0, it's still possible to interpret this double integral as the volume of the solid that lies above D and under the surface z equals f of xy. That's the graph of f. All of this should make sense based on the following picture, and just keeping in mind that the double integral over R of big F is the volume under the graph of f. So here we have some graph of f that lies above some region D. We really should be thinking about this graph of capital F. When we're outside of D but inside the rectangle, then big F takes on the value of 0. So there won't be any volume under that portion. Notice that F really is almost certain to have discontinuities at the boundary points of D along the edges. But it's actually possible to prove, at least in an advanced calculus class, that as long as your function is continuous on D and that the boundary curve of D is nice, whatever that means, then you can prove that the double integral over R of big F exists, and therefore the double integral over D of little f also exists. And this is going to be the case for two types of regions. We're just going to talk about the first type here. Later on, we'll talk about the second type. So a region is said to be a type 1 region if it lies between the graphs of two continuous functions of x. That is, we can say that D is the set of all points x and y where the values of x are between a and b, and the values of y lie between the two functions g1 of x and g2 of x. And we'll assume that g1 and g2 are continuous functions on the interval from a to b. Let's look at some examples of some type 1 regions. Here's a type 1 region. You see the upper and lower bounding curves. Here's another type 1 region. Again, you see an upper and a lower bounding curve. They are continuous functions, so those are nice curves. Here's another type 1 region. You've got an upper and a lower bounding curve. Let's give a method for evaluating a double integral over a type 1 region. Let's say that f is a continuous function on a type 1 region D, the same sort of description that we gave before, then in order to evaluate the double integral over D of f, we'll compute an iterated integral from a to b of the integral from g1 of x to g2 of x of f of xy dy dx. So the inside integral is a dy integral, the outside integral is a dx integral. This is the picture that illustrates what's going on when evaluating a double integral over a type 1 region. D is the region of integration. Y equals g2 of x is the upper bounding curve, that's this right here, and y equals g1 of x is the lower bounding curve, that's this right here. The blue rectangle is the rectangle that we're enclosing this region inside of. Now that iterated integral we get is actually pretty similar to the ones when we were just integrating over rectangles. Notice now that in the inner integral we have to do two things. We'll regard x as being constant, not just in the function, but also in the limits of integration. In the coming videos, we'll show some examples of how to compute some integrals over type 1 regions, and then of course we'll move on and talk about what's known as a type 2 region. Okay, that's all for now.